Hello everyone, my name is Dr. Amit Kumar Yadav. I am going to present one lecture on statistical machine learning. I am assistant professor at School of Computer Science and Artificial Intelligence, SR University, Warangal, Telangana, India. Now first we will see what do we mean by sparsity. It refers to large proportion of zero or empty element in data or model representation. Sparse data or model are those models in which most entries are zero. It focuses only on relevant features or connection. It is found in various contexts such as feature vectors, matrices, and modal pairs. It is a powerful concept for improving model efficiency, interpretability, and computational performance when we are dealing with high dimensional data. In statistical machine learning, sparsity is about focusing on, say, meaningful, relevant data while ignoring the rest. So, in another word, you can say that sparsity is used to focus on, say, relevant data. This lead to efficient, interpretably, and robust model that perform well in, say, high dimensional and computationally intensive setting. High dimensional data and role of sparsity. High dimensional data, it refers to data with large amount of features. Say here dimensions relative to number of observation. It is common in field like say genomic, text processing, image analysis and recommendation system. High dimensional data set poses challenges for machine learning models due to curse of dimensionality, which lead to overfitting, computational inefficiency, and difficulty in model interpretation. Role of sparsity in high dimensional data. It plays a crucial role in making high dimensional data manageable and efficient for machine learning. It reduces computation. It stores only the non-zero element which significant reduce memory usage and speeding up computation. In our bag of word example, instead of processing all 50,000 words, we only focus on the 100 present in the document, making calculation more efficient. Improving model interpretability. Sparsity help model to focus on subset of important features so it can be more interpretable. By removing irrelevant or redundant features, sparse model is simple and explainable. It reduces overfitting. High dimensional data can cause model to overfit learning noise in the data set instead of say two patterns. Sparse data focus on most important dimension results in reducing model complexity and it prevent overfitting in the data. Therefore, performance of model is improved. Feature selection and dimensionality reduction. Due to sparsity, dimension reduction take place by identify and removing less informative features. For feature selection, techniques such as principal component analysis, it is called as PCA, singular value decomposition called as SVD, and feature selection method are used. It can reduce high dimensional data while retaining key information. It enables algorithm to handle high dimensionality. Here we are using certain algorithm like k nearest neighbor, it is called as KNN, or clustering algorithm, struggle with high dimensional data because distance metrics become less meaningful. Sparse representation allow algorithm to operate effectively by reducing the number of, say, dimensions. Now we will see some basic example of sparsity. Consider a simple data set representing the rating given by users to various movies where a 0 indicate no rating was given. So here we are having user A, and user A you give to rating, say, movie 1 5, movie 2 0, movie 3 0, and movie 4 4. And user B used to give rating on, say, movie 1 0, movie 2 3, movie 3 0, movie 4 0. And user C used to give rating on movie 1 2, movie 2 0, then movie 3 0, then movie 4 5. And user D used to give rating on movie 1 0, movie 2 4, movie 3 0, and movie 4 0. Now, each cell represents a rating from 1 to 5 or a 0 for not rating. Many cell contains 0, making this a sparse matrix. If we calculate sparsity of this matrix, so here we are having, say, total elements, say 4 cross 4, that will be equal to 16. Non-zero element, here we are having 5, means rating provided. Therefore 0 element we are having, say, 16 minus 5 is equal to 11. Then sparsity is then defined as ratio of 0 element to total element. How we can write sparsity is equal to number of 0 element by total number of element. So here when we put all this value, so 11 by 16, so we are getting here, say 0.69 or 69%. What it means? It indicates 69% of data is sparse, meaning a majority of the matrix contains no informations. Basis pursuit. What do you mean by basis pursuit? It is used to find out a sparse solution to an underdetermined linear system. In another one word, suppose we are having a set of linear equations where there are more unknown than equation. In that case, basis pursuit looks for a solution that has the fewest non-zero element, is as sparse as possible. Problem formulation. Suppose we have an underdetermined system. It is represented by Ax is equal to B, where A is m cross n matrix with m is less than n. So here fewer equation unknown. Okay, x is the vector of unknown, b is observed data, b is observed data. So here how we can write this, the basis pursuit problem is typically formulated as minimizing the L1 norms of X. It is called as say sum of absolute value of X elements, and it is given by say minimization of X here, here X1 subject to AX is equal to B. This objective increase sparse solution because minimizing the L1 norms tends to produce many zeros in X. Example, suppose we have A is equal to here 1, 1, 1 and here 2, 1, 0, 1. Again we are having matrix B is equal to 4, 3. So here there are more unknown than equation. So four unknown, two equation. So therefore we can use here say basis pursuit would seek a sparse X that satisfy this system as closely as possible. Now here lasso. Lasso means least absolute shrinkage and selection operation. It is a regression method that look like say basis pursuit. It promotes sparsity. However, it is used in say supervised learning context where we want to predict target variable y from a set of features x. This the lasso penalty help in feature selection by shrinking some of the regression coefficient to zero, effectively selecting a subset of the features. Here problem formulation, given data x is an element of R and target value y is an element of R. The lasso optimization problem is given by this equation. Here this term is called as residual sum of square. It measures a prediction error. This term here is a L1 norms of coefficient vector beta. Here lambda is a tuning parameters control amount of regularization. Control amount of regularization. Higher lambda increases penalty, promoting sparsity by shrinking some coefficient to 0 by shrinking some coefficient to 0. So here in this equation, this lambda is a called as a tuning parameters. It controls the amount of regularization. So once we increase this lambda, the penalty will get increases. So here example, suppose we have a data set with three features and a target variables. So this is shown in the matrix, say X here. Here we are having three features and say target here. If we apply here say lasso regression to this data, with an appropriate lambda, the solution beta might shrink some coefficient to 0, effectively selecting only a subset of feature to predict y. Key difference objective say basis pursuit seek the sparse sets solution without necessarily fitting a target variables, while lasso is a supervised method aimed at fitting a target with sparsity promoting regularization. Use case, it is used in say signal processing for sparse signal recovery, while lasso is used in statistics and machine learning for feature selection in regression problem. Next here, say greedy algorithm for sparse linear regression. Greedy algorithm is a say iterative method and it is a part of say sparse linear regression. Its aim is to find a subset of features that best predict a target variable. This is called as greedy because at each step this algorithm make a local optimal choice to add or remove features with goal of building a sparse model with good prediction power. So this greedy algorithm are say faster than more complex optimization method like LASSO and are say particularly useful when computationally efficiency is a priority. The key algorithm for sparse linear regression. First one say forward selection, second one say backward elimination, third one say stage wise regression, next one say here forward selection. So we will see forward selection, initialize with no features. Step 2, find the features that has the highest correlation with the residual. Residual means here difference between predicted and actual value. Step 3, add these features to the model and recompute the residual based on the updated model. Then in step 4, we have to repeat step 2 to 3 until the stopping criteria is met. Example, a desired number of features, a low residual, or a minimum error improvement. Suppose we are having a data set with feature x is equal to x1, x2, x3 and target y. Here simplified outline of how forward selection might work. Initial residual, first of all start with no features. The residual is y. Then we have to select features. Here we have to find out correlation of y with x1, x2 and x3. Suppose x2 has highest correlation with y, updated model, add x2 to the model, compute the coefficient for x2 and update the residual. Then here we have to again here repeat. Check if additional features are needed. It is based on residual reduction or stopping criteria. Then here numericals. Let us say we have a data set with three potential features x1, x2 and x3 and a target variable y. We have to build a linear regression model that best predict y using a subset of these features. So here features row 1, row 2, row 3, row 4. So x1, x2, x3, these are say three features and here we are having say target variable y. So on these features and target variable we have to develop a linear regression model. Then we are having step by step forward selection process. Here start with empty model with no feature selected. Evaluate each features individually. Fit a simple linear models with each features separately to predict y. Once we fit the simple linear regression model with each features, then we have to calculate mean square error or R square error for each models. Let us assume following error called as a mean square error for each single model. Suppose we are getting mean square error for feature x1 as 6 and mean square error for feature x2 as 4 and mean square error for feature x3 as 5. So here we will see x2 has a least value of mean square error. So add x2 to the model. Add x2 to the model. Next, add the next best feature. Now we have a model with x2. Next, we evaluate adding x1 and x3 to this model at one time. Model with x2 and x1. Then we are having mean square error 3. Model with x2 and x3. We are having mean square error 3.5. So now here we will see best features to add x1, lowest combination MSC when combined with x2. Now our model include x2 and x1. So from these two features, say we will see which features combination is having less value of say mean square error. So here we will see features x2 and x1 is having MSC is equal to 3 and model with x2 and x3 MSC is equal to 3.5. Step 4. Evaluate adding the final features. With both x2 and x1 in the model, we check if adding x3 improve performance. So now we will see model with x2, x1 and x3 mean square error is equal to 2.9. Since mean square error decreases further by adding x3, we add to the model. So therefore at this point we can see that by addition of features we have to decide what is the value of say mean square error. So based on those values we have to decide which one is say relevant features to the model. Final models here the forward selection process in with all features x1 x2 and x3 in the models. Since each addition improves the model performance, the final model include all three features. Summary: the forward selection process for this example yield the final model with all features x1, x2 and x3 as each added feature reduces the mean square error. Backward elimination. The algorithm start with all features in the model and we iteratively remove the less significant features. Less significant features means the one with the smallest effect on the target. The steps of backward elimination are say start with all features. Step 2, fit a model using all features. Step 3, identify the features with smallest contribution to the model. often using statistical significance or coefficient. Then in step 4, remove these features and refit the model. Step 5, here we have to repeat step 2 to 3 until a stopping criteria is met. Example, a maximum number of features, a minimal error increases, or a target sparsity level. So here we will see it with example. For a data set, say having x bits element x1, x2, x3 and x4 and target y. Start by fitting a model with x1, x2, x3 and x4. Remove least significant. Suppose x4 has the smallest coefficient or statistically significance. Remove x4 from the model. Refit and repeat. Continue removing the least significant features until stopping criteria is met. Suppose we have a data set with three features, say x1, x2 and x3, and a target variable y. Our main objective is to develop a multiple linear regression model to predict y using these features. So here in features, it is shown by row 1, row 2, row 3, row 4. X1 say 2, 1, 3, 4. And for X2 we are having 4, 2, 6, 8. X3 we are having say 3, 5, 7, 8. And target variable we are having 10, 8, 15, 18. Now, steps in say backward elimination. Step 1, fit the four models with all features. Then start with regression model that include all features, say x1, x2 and x3. After fitting the model, we calculate the row value for each feature's coefficient. These row values tell us the likelihood that each feature's relationship with y is due to chance. Suppose we get the following row value, say x1 row value we are having say 0.08, x2 row value we are having say 0.01, x3 row value we are having say 0.20. Now set the significance level. Choose a significance level, usually say 0.05. Let's say it is 5%. Any features with row value above 0.05 is considered significant, is considered insignificant, and is candidate for removal. Then remove the features with highest p-value. So from features we have to see which features is having highest p-value. Among those features above the significant level, say 0.05, here x3 has the highest p-value of say 0.20, which is greater than 0.05. So we remove x3 from the model. After this, we have to refit and recalculate row value. Now fit model again only x1 and x2. After refitting, suppose we get updated p-value for feature x1 as say 0.04 and for feature x2 we are getting row value as say 0.02. Both row value are now below 0.05, indicating that both x1 and x2 have a statistically significant relationship with y. Stop the process. Since uh, since all remaining features have row value below significant level, therefore we stop backward elimination process. After completing, say, elimination, this final model includes, say, x1 and x2, as they both have a significant impact on predicting y according to the chosen significant level. Then, how we have to find out, say, model performance measure. In machine learning, model performance measures help us evaluate how well a model makes prediction on unseen data. So here are some common metrics. So first one, say, mean absolute error. It measures average magnitude of error between predicted values and measured value without considering their direction. So how we can write mean absolute error? It is given by 1 by n. Summation of I is equal to 1 to n mod of y minus y cap. Here, suppose we have actual value, say y is equal to 3 minus 0.527, and predicted value y cap is equal to 2.5, 0.0, and say 2 and 8. So how we can calculate, say, mean absolute error? So try to see here. Here n is the number of data sample. So in this matrix we are having number of data samples, say 1, 2, 3, 4. So here we should write 4. Here 3 minus 2.5 plus minus of 0.5 minus 0 plus, say, mod of, say, 2 minus 2 plus 7 minus 8. So when we compute this, we are getting, say, 0.5. What are interpretation? On average, the model prediction are zero point 0.5 unit away from actual value. Next, here we are having, say, mean square error. It measures the average of square difference between, say, predicted and actual value. It penalizes large error more. So here mean square error, that will be equal to 1 by n summation of, say, I is equal to 1 to n yi minus yi predicted whole square. So we are taking the same data, and we are calculating the mean square error, and we are getting here, say, 0.375. How we can interpret this one? On average, the squared error in prediction is 0.375 unit. So this penalizes large error more than mean absolute error. Then we are having, say, root mean square error. So the square root of mean square error given the error in the same unit as the original value. The root mean square error, that will be equal to the root 1 by n summation of I is equal to 1 to n in bracket yi minus yi cap whole square. So this value we have calculated. So we have to find out this RMSE, that will be 0.612. How we can interpret this one? It is RMSE is more sensitive to large error than mean absolute error, and indicate the average magnitude of a prediction error. R squared, called as a coefficient of determination. It represents proportion of the variance in the dependent variable that is predictable from independent variable. independent variables, it is given by say r square 1 minus summation of I is equal to 1 to n yi minus yi cap whole square, then by summation of yi minus y bar whole square. What is meaning of y bar? It is mean of actual value. So we are utilizing the same data sets and we are calculating this r square value. We put all this data at its say original place and we are getting here say 0.92. An interpretation r square value of 0.92 suggests that 92% of variance in y can be explained by the model. Then here we are having say classification model performance measures. Suppose we have a binary classification model predicting whether a person has a disease. The actual label and predicted label are shown below. So here data points are shown from say 1 to 8. Here actual is called as true label, predicted is called as a predicted label. Here you will find out positive, negative, okay, and here and in predicted label we are also having positive, negative, negative, positive in this way. Now, using this data, we have to construct a confusion matrix. So, how we will consider a confusion matrix? Say actual positive, predicted positive. So here, true positive, how much? 3. Predicted negative, here 1 is false negative. Then actual negative, 1 is say false positive and 3 is say true negative. Now accuracy is equal to true positive by true negative by total samples. Now how we can calculate the accuracy? That will be equal to true positive 3 plus 3 by 8, that will be equal to 0.75. Interpretation: model correctly classifies 75% of the case. Precision: that will be equal to say true positive by true positive plus false positive. How we are calculating the precision? True positive 3 by true positive plus false positive, 3 by 3 plus 1, that will be equal to say 0.75. Interpreted son, out of all positive prediction 75% were correct. Recalls, so here formula, recall is equal to say true positive by true positive plus false negative. So here recall is equal to say 3 by 3 plus 1 is equal to say 0.75. Interpretation: the model correctly identify 75% of actual positive cases. F1 score, here formula, F1 is equal to 2 into precision into recall by precision plus recall. So we have calculated these parameters. So we are getting here 0.75. What we interpret from this one? F1 score balance precision and score, and it is a 0.75 in this case, indicating good performance. Then how we have to calculate this specificity? True negative by true negative plus false positive. 75% of actual negative cases. Thank you.